Hello pre-calculus students, and welcome to a video that introduces trig identities. Okay, so the point of this is to introduce what an identity is and then to talk about the four basic types or most fundamental types of trig identities. Okay, so first of all, let's just contrast what an identity is versus what an equation is. So in essence, an identity is when you have two sides of an equation that are going to be the same for all values of the input, while an equation is something that's the two sides of the equation are not true for all values of the input. For example, in this trig equation, if you put something like 45 degrees or pi over 4, yes, you'll get the same output. You'll get rad 2 over 2 for both. But if you put something like 30 degrees or pi over 6, you're going to get a 1/2 for the sine and a rad 3 over 2. They're not equal. So they're only equal sometimes, not all the time. And that's sometimes called a conditional identity also, but we've just been calling them equations. With an identity, it's going to be the same for everything. So if I were to graph these two here, they're going to just lay right on top of each other. If I were to put the graph of the secant of theta and then the graph of 1 over the cosine of theta, you wouldn't even tell that there's two graphs. It just looks like one graph. If I put the graph of sine of theta and cosine of theta, they're definitely shifted over from each other and they intersect at certain points. Those are the solutions, but it's not all real numbers. Okay, so trig identity is just basically an equation that is true for all defined values of the input. Okay, there's four different types of fundamental trig identities. Quotient identities, reciprocal identities, Pythagorean identities, and then the even-odd identities. I'm going to start with a brief discussion of the Pythagorean identities because they're super important and they're probably the least familiar at this point. Okay, so we're going to start by just making an angle in standard position, and we'll just make it a first quadrant angle for simplicity, and that's angle theta. And we're going to say that the end, or some point on the terminal side of the angle, is the point x, y. And if that's the case, then this would be the x value and this would be the y value of a right triangle. And we'll just call this the radius of that triangle. You could call it h for hypotenuse, but we're just going to stick with r. All right, Pythagorean theorem tells us that x squared plus y squared is equal to r squared. And also the definition of the sine and cosine tells us that the sine of theta, which is opposite over hypotenuse, is y over r, while the cosine of theta, which is adjacent over hypotenuse, is x over r. Okay, so we can rewrite this by solving for y. So this tells us also that y equals r sine of theta. And we can write this one solving for x, which tells us that x equals r cosine of theta. And now we can just plug those two things into the Pythagorean theorem. So our x squared plus y squared equals r squared will become r cosine of theta squared plus r sine of theta squared equals r squared. Okay, so where does this lead us? Well, when we square, this is two things. This is an r times the cosine of theta, both being squared. So we're going to write this as r squared times cosine squared of theta. And by the way, this notation, cosine squared of theta, this just means the cosine of theta all squared. So we don't have to bother with the parentheses. We just kind of write that exponent in there next to the cosine. It's not the same thing as just the cosine of theta squared, because in this case, this one means that you're squaring just the theta. This one means you're squaring the cosine of theta, and so does this. So these are the same. This one is not the same thing. Okay, so we can rewrite this one as plus r squared sine squared of theta equals r squared. Go ahead and divide both sides of this equation by r squared, and we end up with the famous and all-important Pythagorean identity, cosine squared of theta plus sine squared of theta equals 1. Okay, that's going to be very useful as we move forward. Okay, so let's look at our identities now, and we've got the 4 different types of identities. We've got the reciprocal identities, the quotient, Pythagorean, and the even-odd identities. We're just going to talk briefly about each one of these. All right, so reciprocal identity is probably the easiest one to understand because you've already learned what, for example, you've learned what the cosecant is based on it being 1 over the sine of theta. And we also know that if the cosecant is 1 over the sine, that means that it follows that the sine is 1 over the cosecant. So we've got our 6 reciprocal identities. Those are the first ones. The page got cut off a little bit here, but we've got 2 quotient identities that we need to know. We've got the tangent of theta, which you can see here, and we've also got the cotangent of theta, which we know is the reciprocal of the tangent, so it's going to be the cosine over the sine, or the cosine theta over the sine of theta. We've got the 3 Pythagorean identities. Only 2 of them showed up here. We've got the one that we just explained, and that's the most basic one. And the way that we get these others is we basically just divide. So if you start out with 1 equals sine squared theta plus cosine squared of theta, and you divide both sides of the equal sign by the cosine squared of theta, like this. Then on the left side, you get 1 over the cosine squared, which is the secant squared. And on the right side, you get sine squared over cosine squared, which is the tangent squared. And then the cosine squared over itself, which is 1. And so that's where this one comes from right here. There's one more, and that's if you took the original Pythagorean identity, sine squared of theta plus cosine squared of theta, and you divide both sides by, instead of cosine squared, you divide it by the sine squared of theta. And when you do that, you get 1 over the sine squared of theta, which is the cosecant squared of theta. Oops. And sine squared over sine squared is 1, and cosine squared over sine squared is cotangent squared of theta. Okay, so there's our 3 Pythagorean identities. And the last type of identities here are the even-odd identities. And for those, I want to just kind of remind you of the graphs of the trig functions here. So here's the graph of the sine, and this is probably the easiest way to understand the even-odd, because we know that an even function is a reflection over the y-axis, and an odd function is a rotation over the origin. So if you look at the sine function, you can kind of see that this function is a rotation of itself around the origin, 180-degree rotation. This point here would come down here, and in fact the whole graph would just rotate on top of itself. Same is true of the tangent, that you can see the rotational symmetry. Same is true of the cotangent, you can see the rotational symmetry. And the same is true of the cosecant. You can see the rotational symmetry. This U shape would come down to this one down here if you rotated 180 degrees. The only 2 that are even are the cosine. So you can see the cosine is a reflection over the y-axis. So this point over here is a reflection. In fact, if we continued the graph, that you would be able to see it more clearly, because this is not centered, but it is an even function. Not only the cosine is even, but so is its reciprocal, its sort of partner, which is the secant. So you can see the secant, this sort of U in the middle, has y-axis symmetry. Okay, so when we look at our even-odd functions, first of all, there's 2 that are missing. We've got the sine, cosine, and we're missing the tangent, which is an odd. And we're missing the cotangent, which is also odd. So the way I usually remember these is that the only 2 that are even are the cosine and the secant, they're reciprocals, and those are the only two even functions, and the rest are odd. And that just sort of helps me to not have to keep referring back to the identity, the list of identities. Okay, I hope you found this video helpful.